this video, we're tackling an essential problem for coding interviews LeetCode issue, that is unique paths. This problem is great for learning dynamic programming techniques. We'll explore three different approaches: recursion, top-down DP, and bottom-up DP. So let's break down this problem step by step and understand how the solutions work. So sit back, relax, and let's dive in. Okay, so firstly, let's look into the problem statement. There is a robot on an M cross N grid. The robot is initially located at the top left corner. That is this corner. We can represent this as what? Grid 0, 0, okay? So here, this is the 0, 0 coordinate, okay? So that's what we meant when it is a grid 0, 0. The robot tries to move to the bottom right corner, which is this one, okay? We can represent this as what? M minus 1 and N minus 1. So if we consider we have this M cross N cells, then obviously our numbering starts from 0, 0, right? So this would be what? M minus 1, N minus 1, okay? The robot can only move either down or right at any point in time. So at any point in time, the robot can take only two possible steps, either this one or this one. Given two integers m and n, return the number of possible unique paths that a robot can take to reach the bottom right corner. The test cases are generated so that the answer will be less than or equals to 2 into 10 power 9. So basically here, they mentioned that they will give a m cross n grid. We just need to return the total number of unique paths that a robot can take to reach the bottom right corner, okay? So very simple, right? So here they also mentioned that we don't need to worry about the overflow. It would be in the range of 2 into 10 power 9. And in example 1, when we have m is equal to 3 and n is equal to 7, that is what 3 into 7 grid. So for that grid, we have 3 rows and 7 columns. So in that case, the output is 28. That means that we have 28 unique paths. So let's look into our example 2, which should give you more idea about this. So this is a very small grid and we can get the whole idea here. So here, if you have a robot here, so what all paths it can take to reach the bottom right corner? I'm just showing only the 3 cross 2 grid. So ignore this part. So if you have just this alone, so that means that it's just like 3 rows and 2 columns, okay? So in this path, like how can it reach to the bottom right corner? So from here to here, it is a one way. From here to here, it is a one way. From here to here, it is a one way. So that means that we have 3 unique paths. So here they also given the same right, down, down. That means this one, okay? And next is down, down, right, which is this one, down, down, right. And next is down, right, down, which is this one, okay? So basically it has only 3 unique paths possible. So what are the constraints here? Our m and n are in the included range of 1 to 100. So that means that in the best case, our m and n would be having only value 1. That is only 1 cross 1 dimension. And then in the worst case, it would be 100 cross 100. Okay, so what should we infer from this, guys? So if we consider this 100 cross 100, this is what 10 to the power of 4. Okay, so this is where in the case of m is equals to n and m and n both are 100. We know that we can perform 10 power 8 operations per second. So to have our solution accepted, we should be having the complexity which is less than or equal to 10 power 8 per second. Okay, that means that our complexity should be less than 10 power 8 operation per second. Okay. So to get the solution accepted, we should think of an approach which can solve this problem in 10 power 8 operations per second. Okay, that is like if we just iterate over all the cells in the grid, that is just like 10 power 4, which is the best complexity we have. And in the worst case complexity, it can go up to only 10 power 8. Beyond that, it would be time limit exceeded. Okay, this is what we should infer from this. So let's look into the boilerplate code. So here we have a unique pass method defined, which takes the m and n. These are the integers and it is the integer. This integer is what the total number of unique paths that a robot can take to reach the bottom right corner. Okay, so let's go to the approaches.
Before we get started, I want to remind you about our exclusive blind spot info post. This carefully curated collection covers essential coding interview problems to help you master the most common patterns and excel in your interviews. Whether you're prepping for FANG level interviews or just sharpening your problem solving skills, these problems will ensure you're ready for anything. Even if the exact questions aren't asked, they cover all the important patterns. So be sure to check out our playlist and stay ahead of the competition.
So firstly, let's look into the brute force approach with recursion. So what is the intention here? So in this approach, we solve the problem recursively by considering 2 choices for each step: move right or move down. Starting from the top left corner, we keep making these choices until we reach the bottom right corner. So this is just translating the question into the solution, right? So they mentioned that at each time the robot can take either down or right. Okay. So we're just considering that and then exploring all possible paths we get. So let's look at algorithm. So define the recursive function with parameters ij representing the current position. So ij represents the current position of the robot in the given matrix cells. Okay, in the given matrix. So basically ij is one cell in this. Okay, so what is step 2? It's a base case one. If we reach the last row, that is I is equals to m minus 1. We have m into n rows, right? But we start counting from 0, 0. So last row would be represented by m minus 1 and the last column is represented by what? N minus 1. So if we reach the last row, that is I is equals to m minus 1, that is this row, we can only move right. So there is only one move left. So that one more would be the unique path here. So here, like basically this row, we can't go this side. This is because it's out of bound. Even if we go out of bound, we don't get a path, right? That's why we have to move only this direction. In that case, we have only one unique path left. So we have to return one in that case. Similarly, in the base case too, if it is the last column, that is j is equals to n minus 1, this column, we move only down. So there is only one more left. So here we can't move right, because it's out of bound of array. So that's why we just move this way and we have only one unique path. So in this case also we have to return one. Now guess what? What is the third base case? If we reach a cell where I greater than equal to m and j greater than equal to n, then it's invalid path. So we have 0 unique paths, right? So basically we start counting from 0th index. That way if you reach any cell where I greater than equal to m or j greater than equal to n, then that would be an invalid index. So that case we have to return 0 because there are no paths, right? So that's why we have to return 0. In step 5, if we are not in the last row or last column, recursively calculate the number of paths by moving right and moving down and summing their results. So basically here this is the sum of the path we are considering. So they mentioned the total number of paths, right? So total is what? The sum only here. So here only two choices we have, right? So when we move right, that means that we are incrementing the column. That is, we are going to next column. So we are making it j plus 1 and keeping the I same. Next thing is what? We can move down. So if we are moving down, we are incrementing the row. That's why we keeping I plus 1 and then keeping the column same. That's why it is I plus 1 comma j. Okay, you got the idea, right? So this is the basically is the problem statement translated into the solution. Okay. So let's look into the code, guys. This is just simple what we discussed with the algorithm. So this is the helper function defined as part of step 1. In step 2, we have the base cases where we use the last row. So here, if it is the last row, as we discussed, we return 1. Similarly, we have the base case where we reach the n minus 1 column. That case also we have to return 1. So I just kept this in the two separate lines, but you can just combine this using the or. Okay, so you can just keep as I is equals to m minus 1 or j is equals to n minus 1. We have to return 1. Okay, so I use that style of coding here. So wherein I use the or condition and join these two cases. So what are these two cases? These are the cases where we reach the bounds. So basically when I is greater than or equal to m or j is greater than or equals to n, we have to return 0 because there are no paths, right? It's all invalid paths. So 0 unique paths. That's why we return 0. So in the step 4, that is like we export the right and left most, right? So that is we need total. That's why we take the sum. So here we have two steps to export. That means like two different paths, right? So we take the sum of these two paths, which is helper of I plus 1 comma j and helper of I comma j plus 1. These are two possible ways we have. So we export these two. Okay, we just return this. Okay, and it recursively calls this, and like it starts processing once it reaches the base case. And that's the definition of our helper function, which is recursive in nature. Okay, so here from the unique paths, we just call helper of 0 0. That means that we just start from the index 0 0. Okay, after that we just keep on exploring by moving right and moving down. Okay, so let's look at the complexities. The time complexities of 2 power m plus n due to the number of recursive calls branching at each step. So if we didn't understand this, I'll just explain you. For each cell, we had two decisions to make. That is, we had to move right or we had to move down. Two decisions for how many things we have to make. We have to make for this number of rows and this number of columns. So it is what just sum of this, right? So basically when you have a power b and a power c, it is the formula we have, right? So basically it will be a power b plus c. That's why we do 2 power m plus n. Okay, so this is the complexity we get. Okay, the space complexity is O of mn. This is for the recursion stack we have. So basically recursion stack maximum depth would be at just till m plus n. After that it starts popping out, right? So basically the maximum it can hold is m plus n only. That's why we have the space complexity of O of m plus 1 for this approach. I got the code ready here. Let me try running this. So this is accepted for these two test cases. Let me try submitting this. So we see that time limit is exceeded and only 37 out of 63 test cases are passed. This is because we have exponential time complexity and it won't be scaled for the larger m and n. So that's why we need to optimize our solution. Okay, so we need to bring down the complexity we have. So let's look into the optimizations. So now let's look into the recursion stack. So basically this would give the idea where the bottleneck in the code. So here in each call to recursive function, we make the two possible moves, right? So that is we move right and we move down. So this is the two steps, and let's consider the example 2, which is having m is equal to 3 and n is equal to 2. So here, as we discussed, we start on the 0th row, 0th column. So that's why first in call is 0 0. Okay, and next this is for moving down. So here we just increment the row, and this is for moving right. We increment the column. So similarly, we have all these calls. Okay, so here when you hit the base case, our actual processing starts. Okay, so now let's take a closer look of this. So here helper 2 comma 1 is called for thrice, and also helper 1 comma 1 is called for twice, and this helper 1 comma 2 is called for twice. Also this helper 3 comma 1 is called for thrice. just within the smaller grid we have too many repetitive subproblems, right? So this result is always unique. That means that when you compute once, you can use it for the next time. So what I'm talking is just a dynamic programming, guys. So you have a recurring subproblems, and all the subproblems have the same result each time. Then we can just reuse this subproblem once it is calculated. So that means that if we cache our result somewhere, then we can just utilize this cache storage instead of computing again, right? So that's the idea, guys. So I'm just talking about this top-down dynamic programming approach where we use the memo. Okay, so this memo stores the already computed results. So once the call comes to the recursive function, we just check in the memo if we have the result stored. So if it is stored, then we just return from the cache. If not, we compute it, store the result in cache, and then we return the result. That's the idea for the given subproblem. Okay. So let's just explore the intuition. So in this approach, we use the memoization to store the results of the previously computed subproblems, thus avoiding the recomputation as we discussed. This reduces the exponential time complexity of the recursion. So basically in recursion, we had to compute each time, right? That would give us the exponential time complexity, and that would be optimized here, okay? So let's look at the algorithm. Just a heads up, later point of video, I just show you with one line of change how can we convert this recursive function to the memoized version. For that, understanding of this algorithm is crucial. Okay, so now let's look at the algorithm. In step 1, we define a memoization table initialized to -1 to indicate the uncomputed cells. So basically, we need something to say that the cell is uncomputed, right? So that's why we initialize the table with dimensions m cross n with all cells filled to -1. So why -1? Because when we compute the particular cell, the minimum valid value it would have is 0. This 0 is for this to indicate this 0 unique pass, right? So that's why we choose -1 to say that this cell is not computed. Okay. Step 2, implement a recursive function helper ij to compute the number of paths from cell ij. Okay, so this is just the same function we had. Next is the same basis we have, just like in case 1 we check if I is equals to m-1 and we return 1. In our next base case is if j is equals to n-1 we return 1. Our next base case 3, which is like we check if I is greater than or equals to m or j is greater than or equals to 1. In this case we return 0, the same as previous approach. Step 6 is something different. So if not a destination, we recursively calculate the number of paths by moving right and down, and then we store the result in the memoization table. So basically here the additional step is storing in the table. This is required because next time we get the call to this same subproblem, we can just return from the cache instead of computing it. That way we are optimizing our solution. So now let's look at the code. So firstly, we define our array, m cross n array. So here each cell is filled with -1. So if you don't get this approach, this is just like a list combination version. So if you have a matrix of 3 cross 2, that means we have this 3 rows and 2 columns. So we can represent this as -1, -1, -1, -1, -1, -1. So all cells filled with -1 here. So here, how can we represent it in form of 2D array? This is just -1, -1, and -1, -1, and -1, -1. So this is the representation. So here what we are doing is -1 into n for range in m. So here n is what 2. So if you do -1 into 2, it would just span up this list. Okay, and then we are doing this in loop for 3 times. So we get this for 3 times. Okay, so that's how we get this memo array for the m cross n dimensions. Okay, so this is the initialization we have, and next we define the helper function as we defined before. So here the base cases remain same. Okay, so basically when I is equals to m-1 we return 1, and same for j is equals to n-1 we return 1, and also for the cases where out of bounds, that is I greater than or equal to m or j greater than or equal to n, we return 0. Okay, so this same as previous approach. And now this is where differentiation happens. So for this case we just check if memo of ij is not equal to -1. If it is not equal to -1, that means that it is a computed cell, right? So that's why we just return this cell value directly. If it is not the case, we compute it, right? So this is just we compute in the same way here, and then we store the value in memo ij. Later point of time, we just return the memo ij. Okay, so that means that we just computing the result and storing in memo ij and then returning the memo ij. Okay, so this is the idea here, and similarly here also we call with 0 indices. Okay, so let's look at the complexities. The time complexity is O of m cross n due to the memoization, where each cell is computed only once. So we have m cross n cells, right, and we are processing each cell only once. That's why it is O of m cross n. Basically here, if the cell is computed once, we just return from the cache, right? This is the O of one step. In that case, we don't have extra computations. We just return the subproblems once it's computed. So it is O of m cross n. Okay. And the space complexity is O of m cross n. This is for the memoization table. Basically, our memoization table would be of O of m cross n dimension, and our recursion stack would also be the in the order of O of m plus n, as we discussed in the previous approach. But among O of m plus n and O of m cross n, which is the higher value, it is O of m cross n, right? So our space complexity in total is the sum of these two, right? O of m cross n and O of m plus n. Okay, but this would be higher and this would be negligible. So basically, if we consider 100 into 100, 100 into higher would be much higher than 100 plus 100, right? So the space complex is totally contributed by your memo table. Okay, so now let's look into how can we change this into the Memoized version with just one line change. We just need to add at cache annotation. So let me try summon this. So this accepts solution, right? So what is the difference here? This at cache annotation exactly does what we do in our table. So basically, if a call comes to this helper function again with the same ij parameters, it will look up in the cache instead of computing again. So it can just return from the cache if it is computed. So that's the idea here. So this accepts solution because we're computing the each cell value only once. So I got the code ready here for the Memoized version using the table. Let me try running this. So this accepts solution for these two test cases. Let me try summoning this. So this is the 100% of the users. Cool, right? Now let's look into the iteration with tabulation approach. So what is the intuition here? The idea behind this approach is to use a DP table to store the number of unique paths to each cell in the grid. The key observation is that each cell except the first row and column can be reached from either the cell above it or from the cell to the left of it. Hence the total number of unique paths to the cell will be the sum of the paths from these two neighbors. Makes sense, right? So basically to reach a particular cell, we have the two options if it is not from the first or first column. Either it can get from here or it from here. Total number of unique paths for this cell is just the sum of unique paths for this cell and this cell, right? So that's the main idea, guys. So we just need to think iteratively here. Okay. So let's go into algorithm. Initialize a 2D DP array of size m cross n. Set the first row and first column to 1 since there is only one way to reach any cell in the first row or first column. So basically, if you're in the first row, what is the way to reach is just to move right? So this is the only unique path possible. So it is filled to 1. Same for the first column. Okay, so if you're here, you can't go this way. You can just continue over this path. So that's why it is 1. Okay. In step 2, loop through remaining cells starting from the second row column and calculate the number of ways to reach each cell as sum of cells above it and cells left to it. Okay. So basically we discussed, right? So for this cell, the only way possible is to come from here or here. So total number of unique paths is what? So number of unique paths for this cell and number of unique paths for this cell. That is the idea, guys. Okay. So in step 3, return the value at the bottom right corner of the DB table, which contains the total number of unique paths to reach that particular cell. So basically for this cell, where would be the value stored? It would be just in the last column and last row, right? So we just need to return dp of m-1, n-1, or we can just say directly -1, So this is the last cell, right? So that's the idea, guys. So basically here we want to know the total number of unique paths to this cell only, right? So for that particular cell, the value would be stored in this cell only. That's why we written that. So here dp of ij will denote the number of unique paths from cell 00 to cell i comma j. Okay. Let's look into the code. Very simple code. So here, as we seen in the previous approach, we just initialize all cells to 1 here. So here this would cover our base cases which we discussed in step 1. So the base case is what? The first one, first column. So if we initialize all cells to 1, then that means that we just initialize first one, first column also to 1, right? So we just covered that here. Okay. That means we just avoiding this extra computation. That means like else like in other case, if we insert this with -1, we have to do another 2 more iterations, right? One for rows and one for column, and we just optimize it and just did it in one go by initialization only. So now step 2 is what? Filling the table bottom up. That means that we have to loop the second row and column. So what is the second row and column starting from? It is from 1 index, right? So that's why we go from 1 index until m-1. So here this is exclusive, right? That's why we get the m-1 rows only, okay? And same for here. We go from 1 to n-1. So for each cell, we calculate the number of unique paths. That is just a summation of these two cells we discussed, right? So for this cell, total number of unique paths would be stored in what? dp of i-1 and j. So basically it's the same column but the previous row. That's why it's i-1 and j. And then for this cell, this is the same row but the previous column. That's why it is i-j-1. Okay. So that's why we just add this. Okay. So at the end, we just return the number of unique paths at the bottom right corner. So basically this cell stores our the value we want to return, right? That's why we just return it. Okay. So what are complexes here? The time complex is O of m cross n because we loop through the entire DP table to fill the number of unique paths for each cell, and we process each cell only once here. So if you do not get this here, we just process the each cell only once, and we have m cross n cells. So the time complex is O of m cross n, guys. And the space complex is O of m cross n because we use a 2D DP table to store the intermediate results. So here we don't have the recursion overhead as well. So that's why the space complex is purely O of m cross n here. Okay. So here we have a little optimization space as well. I got the code ready here. Let me try running this. So this is the accept solution with the two test cases. Let me try something this. So this accept solution for all the test cases and with the 100% of users. Cool, right? And thus a wrap on solving the unique paths using three different approaches.
If you found this breakdown useful, drop a comment below and share your thoughts. Don't forget to like the video, spread the word to your fellow coders, and hit the subscribe button for more in-depth coding tutorials. Also, do follow on Instagram for the latest updates. And if you're looking for resources or have some doubts and want to discuss, join our Telegram community. See you in the next one.